Up to now, we've been getting to know Puppet's syntax and understanding the different resources available. It's now time for the next step, trying out some Puppet rules on our local computer. In an earlier video, we called out that Puppet is usually deployed in a client-server architecture. But that's not the only way we can use Puppet. We can also use it as a standalone application run from the command line. This is common when testing new configurations, and it can be the preferred configuration for complex setups, where connecting to a master is no longer the best approach. When using a standalone Puppet, the same computer processes the facts, calculates the rules that need to be applied, and makes any necessary changes locally. So, to get started with our Puppet deployment, let's first install Puppet, and then we can start experimenting with running rules locally. In later videos, we'll check out how to create a client-server deployment. As we've called out, Puppet is available on a number of different platforms. We can either install it from the package management system available in the OS, or download it from the official website. Both options work fine, and the best one to choose will depend on our specific needs. For this exercise, we'll just go with the Puppet packages provided by the Ubuntu distribution. We'll do that by installing the Puppet master package using sudo apt install puppet master. All right, we now have the package installed and can start trying out a few rules. We'll begin by creating the simplest possible Puppet file. We can make it more complex as we improve our deployments. For this example, we want to use Puppet to make sure that some useful tools for debugging problems are installed on each computer in our fleet. To do this, we first have to create a file where we'll store the rules that we want to apply. In Puppet lingo, these files are called manifests, and they must end with the .pp extension. So, we'll create a new file called tools.pp, and in this file, we'll create a package resource. We'll start by managing the htop package, which is a tool similar to top that can show us some extra information. We'll state that we want Puppet to ensure that we have this package present on our computer. Cool, that was simple. That's all we have to do. This resource will take care of installing the package for us. Let's save the file and try it out. But before actually applying the rules, we want to check that the command isn't present yet. Right, htop isn't installed yet. Let's fix that by running our rules using sudo puppet apply-v tools.pp. The -v flag tells Puppet that we want to get verbose output, which will tell us what's going on while Puppet is applying the rules in the file that we pass to it. So here, Puppet first told us that it was loading the facts, then that it compiled a catalog. After that, it told us that it was applying the current configuration, then that it installed the package we requested, and finally, it let us know that it finished applying this catalog. You're probably wondering, what's a catalog? We called out in an earlier video that after loading all facts for a computer, the server calculates which rules actually need to be applied. For example, if a package should only be installed when a certain condition is met, this condition is evaluated on the server side based on the gathered facts. The catalog is the list of rules that are generated for one specific computer once the server has evaluated all variables, conditionals, and functions. In this example, the catalog will be exactly the same as our code because the code didn't include any variables, functions, or conditionals. More complex sets of rules can lead to different catalogs depending on fact values. It's now time to check if our rules actually worked. Let's try running the htop command again, now that Puppet has installed it for us. Yes, this time it worked. If our computer was misbehaving, we could now use this tool to get a better idea why. But fortunately, our computer's on its best behavior, so we'll exit now using Q. Let's see what happens if we try to apply the Puppet rules again now that the package is installed. Ha! Puppet's smart. It noticed that the package is already installed, so it didn't try to install the package again. This means it applied the catalog much faster because nothing had to be changed. We've now seen how to write a Puppet resource in a manifest file, and then use Puppet apply to apply those rules to one computer. Up next, we'll check out how we can manage relationships between different Puppet resources, and what that looks like when applied. In our last video, we wrote a very simple manifest, which we then applied locally. That was a great way to practice applying Puppet rules, but it was super simple. Let's challenge ourselves with something a bit more tricky. The Puppet manifests that we use to manage computers in our fleet usually include a bunch of different resources that are related to each other. You're not going to configure a package that's not installed, and you don't want to start a service until both the package and the configuration are in place. Puppet lets us control this with resource relationships. Let's check this out in an example. We have a file called ntp.pp that has a bunch of resources related to the NTP configuration, like the one we've seen in an earlier video. This time, on top of declaring the resources that we need to manage, we're also declaring a few relationships between them. We say that the configuration file requires the NTP package, and the service requires the configuration file. This way, Puppet knows that before starting the service, the configuration file needs to be correctly set, and before setting the configuration file, the package needs to be installed. We're also declaring that the NTP service should be notified if the configuration file changes. That way, if we make additional changes to the contents of the configuration file in the future, the service will get reloaded with the new settings. If you look closely, you might notice that the resource types are written in lowercase, but relationships like require or notify use uppercase for the first letter of the resource. This is part of Puppet's syntax. We write resource types in lowercase when declaring them, but capitalize them when referring to them from another resource's attribute. If this sounds confusing right now, don't worry. It might take a while to wrap your head around it, but it will eventually click. Now, one last thing. At the bottom of the file, we have a call to include NTP. That's how we tell Puppet that we want to apply the rules described in a class. For this example, we put the definition of the class and the call to include the class in the same file. Typically, the class is defined in one file and included in another. We'll check out examples for this in later videos. All right, let's apply these rules locally. Great, our rules have run, and in the verbose output, we can see that it did a bunch of things. First, it installed the package. Then, it checked that the configuration file needed to be updated, and so it changed its contents. Finally, after changing the contents of the configuration, Puppet knew to restart the NTP service. We see here how our Puppet rules have translated into a few different actions. That's cool, but it's about to get even better. Let's make a change to the configuration file by editing the ntp.conf file in this directory. This is the configuration file used by the NTP service. It's currently using a bunch of servers from ntp.org, but instead of those servers, we want to try out the NTP servers provided by Google. These are called time1.google.com, and then time2, time3, and time4. All right, we've made the change. We'll save with :wq, and then rerun our Puppet rules with the new configuration file. Awesome. Puppet updated the configuration file with the new contents, and then refreshed the service so it loaded the config. Success! In this video, we've seen how we can apply a Puppet manifest that includes a class with a bunch of resources. We grouped all of the information related to the NTP service in a manifest specific to it, which is common practice when dealing with Puppet rules. We want to keep related operations together and separate things that are unrelated. Up next, we'll look into how we can do that using Puppet modules. In any configuration management deployment, there's usually a lot of different things to manage. We might want to install some packages, copy some configuration files, start some services, schedule some periodic tasks, make sure some users and groups are created and have access to specific devices, and maybe execute a few commands that aren't provided by existing resources. On top of that, there might be different configurations applied to the different computers in the fleet. For example, workstations and laptops might include resources that aren't used on servers, and each distinct type of server will need its own specific setup. There's a lot of different things to manage. We need to organize all these resources and information in a way that helps us maintain them long term. This means grouping related resources, giving the groups good names, and making sure that the organization will make sense to new users. In Puppet, we organize our manifests into modules. A module is a collection of manifests and associated data. We can put any resource we want into a module, but to keep our configuration management organized, we'll group things together under a sensible topic. For example, we could have a module for everything related to monitoring the computer's health, another one for setting up the network stack, and yet another one for configuring a web serving application. So, the modules ship the manifests and the associated data, but how is this organized? All manifests get stored in a directory called manifests. The rest of the data is stored in different directories depending on what it does. The files directory includes files that are copied into the client machines without any changes, like the ntp.conf file that we saw in our last video. And the templates directory includes files that are pre-processed before they've been copied into the client machines. These templates can include values that get replaced after calculating the manifests, or sections that are only present if certain conditions are valid. There's a bunch more directories that can be part of a module, depending on what exactly the module does. But you don't need to worry about these when creating your first Puppet module. You can start with a simple module that just has one manifest in the manifest directory. This file should be called init.pp, and it should define a class with the same name as the module that you're creating. Then, any files that your rules use need to be stored in the files or templates directories, depending on whether you copy them directly or need to pre-process them. For example, this is how the NTP class that we saw in our last video looks like when turned into a module. There's an init.pp file, which contains the NTP classes that we saw before. And the ntp.conf file that gets deployed onto the machine is now stored in the files directory. Modules like these can look pretty much the same no matter who's using them. That's why, over time, system administrators using Puppet have shared the modules they've written, letting others use the same rules. By now, there's a large collection of prepackaged modules that are shipped and ready to use. If one of those modules does what we want, we can just install it on our Puppet server and use it in our deployments. Let's install the Apache module provided by Puppet Labs to check out how this works. Okay, we've installed the module. Let's have a quick look at its contents. First, we'll change into the directory where the module files are stored and list its contents. We see the files, manifests, and templates directories that we mentioned. On top of that, there's a lib directory that adds functions and facts to the ones already shipped by Puppet. And the metadata.json file includes some additional data about the module we just installed, like which versions of which operating systems it's compatible with. Let's peek into the manifests directory. Whoa, that's a lot of files. Kind of like how we split the different things that we want to manage into separate modules. We can also split each separate functionality that we want to configure into separate manifests. This helps us organize our code when we make changes to it. And see how this directory also contains its own init.pp? As we called out, this manifest is special. It needs to always be present because it's the first one that's read by Puppet when a module gets included. So, how do we include a module like this one? It's pretty easy. Let's create a manifest file that includes the module we just installed. Here, we're telling Puppet to include the Apache module. The double colon before the module name lets Puppet know that this is a global module. Let's save this file now and apply it using Puppet apply, like we did before. Our manifest was super simple. It just included the Apache module. But by including the module, we got Puppet to apply all the rules run by default in the module. We now have an Apache server configured and ready to run on this machine. Handy, right? Okay, we've just seen how we can organize our code in modules and how we can even use modules provided by other teams so we don't have to reinvent the wheel. When managing fleets of computers, we usually want some rules to apply to every computer and other rules to apply only to a subset of systems. Let's say you're managing all your servers with Puppet. You might want to install a basic set of tools on all of them, but only install the packages for serving web pages in your web servers, and only install the packages for sending and receiving email in your mail servers. There's a bunch of different ways that we can do this. In an earlier video, we saw how to conditionally apply some rules using facts from the machines. Another way to apply different rules to different systems is to use separate node definitions. In Puppet terminology, a node is any system where we can run a Puppet agent. It could be a physical workstation, a server, a virtual machine, or even a network router, as long as it has a Puppet agent and can apply the given rules. So, we can set up Puppet to give some basic rules to all the nodes, but then apply some specific rules to the nodes that we want to be different. Let's check out an example of how this could look. When setting up Puppet, we usually have a default node definition that lists the classes that should be included for all the nodes. For example, it could look something like this. Here, the default node is including two classes, the sudo class and the NTP class. For the NTP class, we're setting an additional servers parameter that lists the servers we can use to get the network time. As you can see here, when defining a node, you can include a class by just using its name if there's no additional settings, or include the class and set additional parameters if necessary. All right, that's the default node, so it will apply to computers in the fleet by default. What if you want some settings to only apply to some specific nodes? You can do that by adding more node definitions that list the classes that you want them to include, like this. We can see here that specific nodes in the fleet are identified by their FQDNs, or fully qualified domain names. In this case, we have the node definition for a host called webserver.example.com. For this node, we're including the same sudo and NTP classes as before, and we're adding the Apache class on top. We're listing the same classes because the classes included in the default node definition are only applied to the nodes that don't have an explicit entry. In other words, when a node requests which rules it should apply, Puppet will look at the node definitions, figure out which one matches the node's FQDN, and then give only those rules. To avoid repeating the inclusion of all the common classes, we might define a base class that does the work of including all the classes that are common to all node types. Now, where's this information stored? The node definitions are typically stored in a file called site.pp, which isn't part of any module. Instead, it just defines what classes will be included for what nodes. This is another step towards helping us organize our code in a way that makes it easier to maintain. Up next, we'll look into the infrastructure used by Puppet to verify if a node really has the name that it claims to have. We've called out a few times that in typical Puppet deployments, all managed machines in the fleet connect to a Puppet server. The clients send their facts to the server, and the server then processes the manifests, generates the corresponding catalog, and sends it back to the clients to apply it locally. In our last video, we mentioned that we can apply different rules to different nodes, depending on their names. The clients send their name to the server when they connect. But how can the server trust that a client is really who it claims to be? It's a dangerous world out there. Well, this is a complex subject that touches on some important security concepts. We'll do a quick rundown here. If you're interested in learning more, you might want to check out the security course in the Google IT Support Professional Certificate Program, led by my colleague Gian, who explains it in more detail. Puppet uses public key infrastructure, or PKI, to establish secure connections between the server and the clients. There's a bunch of different types of public key technologies. The one used by Puppet is Secure Sockets Layer, or SSL. This is the same technology used for encrypting transmissions over HTTPS. The clients use this infrastructure to check the server's identity, and the server uses it to check the client's identity. And all communication is done over an encrypted channel that uses these identities, so it can't be intercepted by other parties. So, how does this work? Each machine involved has a pair of keys related to each other, a private key and a public key. The private key is secret, only known to that specific machine. The public key is shared with other machines involved. Machines can then use a standardized process to validate the identity of any other machine. The sender signs a message using their private key, and the receiver validates the signature using the corresponding public key. Okay, but how do machines know which public keys to trust? This is where a certificate authority, or CA, comes in. The CA verifies the identity of the machine and then creates a certificate stating that the public key goes with that machine. After that, other machines can rely on that certificate to know that they can trust the public key, since it means the machine's identity has been verified. Puppet comes with its own certificate authority, which can be used to create certificates for each client. So, you can use that one, or if your company already has a CA that validates the identity of the machines in your fleet, you can integrate it with Puppet, so you only validate the identities once. Now, let's assume you're using the baked-in certificate infrastructure, and dive into how this process works. When a node checks into the Puppet master for the first time, it requests the certificate. The Puppet master looks at this request, and if it can verify the node's identity, it creates a certificate for that node. The system administrator can check the identity manually, or use a process that does this automatically using additional information about the machines to verify their identity. When the agent node picks up this certificate, it knows it can trust the Puppet master, and the node can use the certificate from then on to identify itself when requesting a catalog. You might be wondering, why do we care so much about the identity of the nodes? There's a bunch of reasons. First, Puppet rules can sometimes include confidential information that you don't want to fall in the wrong hands. But even if none of the rules hold confidential info, you want to be sure that the machine you're setting up as your web server really is your web server, and not a rogue machine that just claims to have the same name. All sorts of things could go wrong if random computers start popping up in your network with the wrong settings. If you're creating a test deployment to try out how Puppet rules get applied, and so you're only managing test machines, you can configure Puppet to automatically sign all requests. But you should never do this for real computers being used by real users. Remember that it's better to be safe than sorry, so always take the time to authenticate your machines. When starting out with Puppet, it's common to use the manual signing approach. In this case, when the node connects to the master, it will generate a certificate request, which will go into a queue in the Puppet master machine. You'll then need to verify that the machine's identity is correct, and the baked-in CA will issue the corresponding certificate. If your fleet is large, this manual approach won't really work. Instead, you'll want to write a script that verifies the identity of the machines automatically for you. One way to do this is by copying a unique piece of information into the machines when they get provisioned, and then use this pre-shared data as part of the certificate request. That way, your script can verify that the machines are who they claim to be without involving any humans. Great. You now have a broad idea of the infrastructure that Puppet uses to identify the nodes when they connect to the master. Up next, we'll see what the typical Puppet setup, using a separate Puppet server and client, looks like in practice. We're now ready to see a Puppet deployment in action. We've already installed the Puppet master package on this computer, so we'll use it as the master. Since this is a test deployment to demonstrate Puppet, we'll configure it to automatically sign the certificate requests of the nodes we add. But remember, if we were deploying this to real computers, we'd have to manually sign the requests or implement a proper validating script. We'll do this by calling the Puppet command with the config parameter and then saying that in the section master we want to set autosign to true. Alright, with that we can connect to the client that we want to manage using Puppet. We'll connect using SSH to a machine called web server. On this machine, we'll install the Puppet client, which is shipped by the Puppet package. Nice, we have the Puppet agent installed. Now, we need to configure it to talk to the Puppet server that we're running on the other machine. To do that, we'll use Puppet config like before, but this time we'll tell it that we want to set the server to ubuntu.example.com. Great. Now that we've configured the server, we can test the connection to the Puppet master by using the Puppet agent command, passing -v as before to get verbose output, and --test to do a test run. As usual, Puppet tells us everything it did. It first created an SSL key for the machine. It then read a bunch of information from the machine and used this to create a certificate request. The agent shows us the fingerprint of the certificate requested. If we were using manual signing, we could use this fingerprint to verify that the request in the server matches the one generated on the machine. The certificate was then generated on our Puppet master. We don't see any entries for that because it happened on the other computer. But we see that this computer received a certificate and stored it locally. Once the certificate exchange completed, the agent retrieved all the information from the machine and sent it to the master. In exchange, it got back a catalog and applied it. The catalog applied almost immediately because we haven't actually configured any rules to be applied to our clients. We should go ahead and do that now. We'll go back to our Puppet master and create a couple of node definitions. As we called out, node definitions are stored in a manifest file called site.pp, which is stored at the root of the node's environment. We'll talk more about environments in a later video. For now, we just need to know that our client is trying to access the production environment. So, the file that we need to create will be located in /etc puppet code environments production manifests, and it will be called site.pp. In this file, we'll create a couple of node definitions. We want to install Apache in our web server, so we'll create a node definition for the web server with the Apache class and no parameters, for now. And we'll also add a default node definition. We'll keep it empty for now. We can add more classes in the future. Alright, with that we have our very basic node definition. We can now save this and run the Puppet agent on our web server machine again. This time, the Puppet agent connected to the Puppet master and got a catalog that told it to install and configure the Apache package. This included setting up a bunch of different services. Up to now, we've been doing manual runs of the Puppet agent for testing purposes. Now that we know it's working fine, we want to keep Puppet running automatically. That way, if we make changes to the configuration, clients will automatically apply those changes without us having to do any manual steps. So to do that, we'll use the systemctl command, which lets us control the services that are enabled when the machine starts and those that are currently running. So we'll first tell systemctl to enable the Puppet service, so that the agent gets started whenever the machine reboots. And then we'll tell systemctl to start the Puppet service so that it starts running. Last up, we'll ask systemctl for the status of the Puppet service to check that it's actually running. Awesome, that worked! The Puppet agent will keep regularly checking in with the master and ask if there are any changes that need to be applied to the machine. And with that, you've seen Puppet in action using the server-client model. We use the configuration we set in the Puppet master to manage the installation and configuration of software in our web server. And we set up the Puppet agent in the web server to keep running so that the configuration stays up to date. We've only seen the very basics of how to configure Puppet, but this can already give you an idea of how powerful configuration management can be. Pretty exciting, right? As we've called out, when we change a manifest modifying a setting that's already managed by Puppet, Puppet applies this change to the nodes. The Puppet agent does whatever's needed to bring the nodes to the new desired state. So you can make a small change in your manifests and have that modify all the machines in your fleet. This is super powerful, but with great power comes great responsibility. In the next few videos, we'll look into how we can test our changes to make sure they do what we want them to do, and then apply them onto our fleet without causing trouble. It's pretty common for IT specialists working on configuration management to test out new rules on their machines by simply forcing the machine to apply the manifests they want to test. We've done this in some of our examples, where we applied the rules locally before applying them to remote machines. This approach can backfire, though. Say you're trying to use Puppet to change the permissions of some files on the nodes, locking down some paths that you don't think that your users will need. Now, imagine you try out the rules on your computer and discover you made a mistake and locked yourself out. Oops. So what can you do instead? There's a bunch of things to consider. A simple first step is to use the Puppet parser validate command that checks that the syntax of the manifests is correct. On top of that, we can also run the rules using the --noop parameter. The name comes from no operations, and it makes Puppet simulate what it would do without actually doing it. You can look at the list of actions that it would take and check that they're exactly what you wanted Puppet to do. But if the change is complex, it's likely that we'll miss something important when looking at the planned actions. Another option you could use is having test machines that are used only for testing out changes. You can apply the rules there, and after Puppet has run, check that everything's working correctly. But again, this is a manual process, and we might forget to verify something important. How can we automate it? Kind of like the Python automatic tests that we checked out in an earlier course, Puppet also lets us test our manifests automatically by using RSpec tests. In these tests, we can set the facts involved to different values and check that the catalog ends up stating what we wanted it to. Let's check out an example. Here, we're setting the isVirtualFact to false. And then we ask the test infrastructure to verify that the GKSU package is included with the ensure parameter, set to latest. Tests like this one can be a useful way to check that our catalog is written correctly. And they can be super helpful when our rules use a lot of facts that interact with each other, and we want to check that the result is actually what we intended. We can write a bunch of these tests and run them automatically whenever there's a change to the rules. This way, we can be sure that the rules stay valid and know that the new changes didn't break the old rules. But that just checks that the catalog contains the rules that we said it should contain. How can we verify that these rules actually have the effects we want, like enabling the corporate website or setting up a strict firewall? We need to apply the rules on the nodes and check that the result is correct. We can automate this process too. To do this, we can use a set of test machines where we first apply the catalog and then use scripts to check that the machines are behaving correctly. Now, let's assume all your tests were successful and the change is ready to be published. How do you push it safely to your whole fleet? Once you've prepared and tested the changes that you want to make, it's time to roll them out. But not so fast. Even if you tested the change on your computer or on a test computer and it worked just fine, it doesn't mean that the change will work correctly on all machines running in production. First, what do we mean by production? In an infrastructure context, Production is the parts of the infrastructure where a service is executed and served to its users. If you host a website, the servers that deliver the website content to the users are the production servers. Inside your company, the servers that validate users' passwords are the production authentication servers. You get the idea. Making changes to the production servers can be tricky because if something goes wrong, the service can go down. So how can we roll out changes safely? The key is to always run them through a test environment first. The test environment should have one or more machines running the exact same configuration as the production environment. But these machines aren't actually serving any users of the service. This way, if there's a problem when deploying the changes, you'll be able to fix it without any actual users seeing it. As we briefly touched on in an earlier video, Puppet has environments baked in. Each environment has its own directory, with its own set of manifests and modules. Puppet environments let us fully isolate the configurations that the agents see depending on what environment they're running. And this isn't just what nodes install which modules, it's also the whole contents of the modules. For example, we can use this to try out a whole new version of the Apache module for the machines in the test environment, while still using the old version for the production environments. You can define as many environments as you need. For example, you could have a development environment for IT specialists to try out new Puppet rules before they even reach the test environment. Or say you're developing a very tricky new feature for your system and you don't know when it'll be ready. You could have an environment for testing just that specific feature. Now, let's assume that you have a bunch of changes ready to roll out. You'll usually push them to the machines in the test environment first and check that everything works well there. This can include both manual verification and automated checking. Okay, say the changes worked fine in the test environment. How do you roll them out to the other machines in your fleet? You might be tempted to just apply the changes to all the machines and be done with it. But pushing changes to every machine at the same time is usually not a great idea. It's always possible that we missed some special case when preparing the change, which wasn't part of our test environment. And suddenly, half our fleet is offline. Oops. So instead of pushing the changes to all nodes, we'll usually do it in batches. There's a bunch of ways you can do this, depending on how your fleet is arranged. You could have some machines with a fact that marks them as early adopters, or canaries. Sort of like the canaries that coal miners use to detect toxic gases in the mines, these nodes detect potential issues before they reach the other computers. So, you could push the changes to the canaries on one day, check that everything's working fine, and then deploy them to the rest of the fleet on the next day. That way, if there's an issue with the changes that wasn't caught in testing, only a subset of the users might see it. As soon as you get notified of the problem, you can roll it back and avoid it hitting the rest of the fleet. Now, we've been talking about changes without going into detail on what those changes are. It's a good idea for these changes to be small and self-contained. That way, if something breaks, it's much easier to figure out where the problem was. Imagine you're trying to push 6 months worth of changes to your fleet of computers. When you push this to the machines in the test environment, you discover that they stop responding altogether. You now need to comb through all the changes that were bundled together to try to find out which one is causing the problem. Yikes. Instead, you could aim to roll out your changes every 1 or 2 weeks. This would mean that whenever a problem is detected, there's only a small list of changes to go through to figure out the culprit. Of course, there's a lot more to say about testing and releasing changes safely. But you don't need to put all the best practices in place to get started. You could start small and make improvements as you go. As your manifests get more complex, you want to improve the automated testing of all the pieces. And as the fleet you manage with your configuration management system grows in size, you'll want to increase the size of your testing environment, move some nodes to canaries, and so on.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.